Match Recognize is a feature of Flink SQL that allows you to describe patterns that are matched against a stream of incoming events. Now, when I first heard about this feature, I thought it sounded rather obscure. But now that I understand it, I do find lots of uses for it. Knowing how to use Match Recognize has been a bit like having a secret superpower. Match Recognize has been part of the SQL standard since 2016, but before I started working with Flink SQL, I had never heard of it. I imagine this is because very few databases have implemented Match Recognize. On the other hand, pattern matching, or complex event processing, is a good fit for many stream processing use cases, and given the popularity of SQL for stream processing, Match Recognize is becoming a widely used tool in the data streaming engineer's toolbox. Now, Apache Flink supports most, but not all of the Match Recognize standard. And Flink does go beyond the standard in one area, which I'll illustrate with an example. This video is organized around presenting some examples of how to use Match Recognize, first for building event-driven applications, and then for computing real-time analytics. I'll close by sharing some hard-earned best practice tips for working with and troubleshooting queries that use Match Recognize. The first couple of examples I want to show you involve detecting patterns in this orders table. In these examples, we'll be using the customer ID, product ID, price, and row time fields, which tell us which customer placed the order, what product they purchased, its price, and the time the order was placed. We're going to start with a relatively straightforward example. The idea will be that we want to identify customers who have just placed a second order for something they have already purchased within the past 60 days. The business requirement might be that we want to invite them to create a subscription that will order this product for them on a regular basis. But let's start by learning to identify the customers who exhibit this pattern. The overall approach with Match Recognize is that we're going to be applying it to an input table, in this case the orders table, and then Match Recognize is going to transform the input into a table of results. Each time the pattern is matched, one row will be appended to the output. Match Recognize works from a description of this transformation, and it consists of two steps. First, a description of what the pattern looks like and how it should be applied to the table, and secondly, what the output is supposed to look like. In this case, I want output that shows which customer placed two orders for the same product, what the product is, and when those orders were placed. The first step in describing the pattern is to determine if and how the input should be partitioned. Partitioning the input is the same as grouping the table rows by one or more of their fields. For example, we could partition the orders table by the customer ID. Since this table currently has orders for two customers, this partitioning will yield two partitions, each having two orders. The patterns you define with Match Recognize are matched independently in each partition. This means that it's best to partition the table as finely as possible, because then each partition will have fewer irrelevant records that your pattern will have to know how to skip over. For this example, partitioning the table by both customer and product will be ideal, because then each partition will have exactly what we need and nothing extra. It'll just have the records for one customer and a specific product. Now we can start to look at the syntax used by Match Recognize. Here's the partitioning we just talked about. And here are the basics of the pattern itself. Patterns are described as regular expressions. Here the pattern is a sequence of two consecutive orders, called O1 and O2. In general, the within clause is optional. In this example, it specifies that the entire pattern must be matched by a sequence of events no more than 60 days long. This time constraint is something the Flink community has added to Match Recognize. It's not part of the SQL standard. The variables used in the regular expression are defined below the pattern spec in a section labeled Define. This section is where you can impose constraints on what these variables can match. In this example, I'm leaving both O1 and O2 unconstrained. They can match anything. Because we have partitioned the input stream by both customer and product, we know these two orders are already constrained to be for the same customer and the same product. For the pattern matching to behave correctly and deterministically, Match Recognize always sorts its input. Flink only supports Match Recognize in streaming mode and can only sort the input stream by the time attribute of the input table. In this case, we are using the row time field provided by Confluent Cloud. Why does Match Recognize need to sort its input? Well, the patterns being matched describe sequences of events, arranged in time. Since event streams often have their events arrive out of order, we need to somehow guarantee that Match Recognize will apply its pattern matching logic to the events in the order in which they originally occurred. The final piece in setting up the input side of Match Recognize is to define where in the input table the pattern matching engine should begin looking for the next match. In this case, we want to position the pattern matcher at the order immediately after O1. This means that O2 will be considered as the first order in the next match. You can make other choices for after match skip. For example, if I use skip past last row instead, match recognize will skip ahead and wait for a row to arrive after O2. Skip to first and skip to last allow for more fine-grained positioning within the matched pattern. In my experience, these options are only rarely useful. Now it's time to skip gears and look at how match recognize allows us to describe the output it's going to produce. For starters, every row in the output will contain the columns used for partitioning. In this example, that's the customer ID and the product ID. Each output row will also contain the columns described in the measures clause. Notice how the variables O1 and O2 that were used to define the pattern are available for us to use here in the measures clause. In this case, I'm using the variables O1 and O2 to define the columns named order 1 time and order 2 time. Those contain the timestamps of the two matching orders. We've now fully described both the input and output sides of this pattern, and here's what the complete solution looks like. The match recognize block in this query holds the pattern definition we've been developing. Match recognize is being applied to the orders table, and we are selecting specific columns from the table produced by match recognize. Now I can hear some of you saying that this all feels a bit overblown, and you'd rather use an over window or a self-join instead. Okay, those are reasonable alternatives. So for comparison, here's what those solutions would look like. For many simple patterns, you will often be able to find another solution, and those other solutions may be perfectly viable. Knowing how to use match recognize becomes much more of a superpower as the patterns become more complex. In this case, both of the queries shown here will optimize their state retention. They won't keep any orders more than 60 days old, and the same is true for the solution based on match recognize. For this use case, the only significant problem I can see is with the self-join, because the self-join can't easily be made to have a time attribute in its output stream. This prevents the join from being used as input to further time-based operations. You would have to first materialize its output to Kafka, and then set up the timestamps and watermarks yourself. Now I want to show you one more thing before moving on to another example. This pattern I've developed is based on partitioning the table by both customer and product. But what if I had left out the product dimension and only partitioned the input by customer ID? The effect would be that each partition would include all of the orders for that customer. To accommodate this, the pattern would need to be more complex, so that it could skip over any orders for other products that might occur between O1 and O2. This idea is captured in the revised pattern by the variable other, where each instance of other is an order for any product other than the product purchased in O1. So in this pattern, other star is similar to dot star, which you would use in a regular expression. In this next example, we are going to look for customers whose orders keep increasing in price, perhaps with the goal in mind of offering them some sort of reward, like an offer for free shipping. Just like the first example, this pattern is also being applied to the orders table, but this time it is partitioned by the customer ID. Once again, it is ordered by the system-provided row time column. Here then is the pattern. It's a sequence of 3 consecutive orders, where the price has gone up each time. The heart of this condition is expressed here, using the last function. Here we are comparing up.price, which is the price of the incoming row, to the price of the previously matched order. If there was no previous order, this price comparison would be false. In general, the last function lets you look backwards through the stack of recently matched records and access the values of their fields. In this case, we are just looking back one record and checking the price of the last order. There is also a first function. It behaves very similarly, except that it starts counting from the first mapped records instead of the last. Last is not well defined when the sequence of matched records is empty, so I've used the highlighted condition to bootstrap the pattern matching. The count is equal to 1 when the first record is being added to the variable up. Once the count is no longer 1, or in other words, once the up variable is no longer empty, subsequent matching orders will need to have higher and higher prices. For this example, I've chosen to produce as output an array containing the prices of the 3 matching orders. I find this array aggregation function really useful. It's especially helpful for debugging and verifying the behavior of your queries. You might be wondering why I had this pattern look for exactly 3 orders with increasingly higher prices. Why not find cases with 3 or more orders with ascending prices? Well, this is how you would express that idea. With a comma after the 3, this pattern will match cases with not just 3, but with 3 or more orders satisfying the conditions. However, if you do try this, you will get the error shown here. Why does this fail? This fails because Flink's implementation of match recognize is designed to produce a final result once the pattern is fully matched. If asked to find 3 or more orders satisfying the condition of ever-increasing prices, then it always makes sense for the pattern matching algorithm to wait for more orders that match the pattern. If the pattern were bounded, then it could wait until it had processed all of the input, and then it could produce its final result. But since the input is an unbounded stream, a pattern like this can never be fully matched. One way to fix this is to allow the pattern to match 3 or more orders with increasing prices, but followed by an order where the price then goes down. Here, down is defined as an order whose price is less than the price of the last order in the group of orders matching the up condition. These examples have illustrated use cases of the kind of complex event processing that match recognize makes possible. Other use cases for complex event processing include fraud and anomaly detection, and business process monitoring. In general, these use cases will trigger some sort of reaction when the stream of incoming events matches some predefined pattern. A complete solution could be built along these lines. Having found a match to one of these patterns, we can then combine the information derived from the pattern with additional contextual information, such as the customer's email address, and write that all out to a Kafka topic that serves as input for a microservice. That service can then send an offer to the customer. But there's another category of applications you can build with match recognize, and that involves using pattern matching for computing real-time analytics. In a previous video, I talked about using window functions with Flink SQL to compute real-time analytics. That included session-based analytics, where sessions were defined by periods of inactivity between the sessions. In this next example, I want to show you how to use match recognize to compute session-based analytics, where the sessions are not defined by event timing, but are instead demarcated by specific events. Many real-world event streams include pairs of events, such as connect and disconnect, or login and logout, that mark the beginning and ending of sessions like this. This example is going to be based on a simulation of a video-on-demand streaming service. This is a very simple, straightforward simulation, but it should be enough to get across the main concepts without getting us bogged down in the details of an imaginary business. Here are some events from one of the simulated users. We can make better sense of these events if we sort them by time, just as match recognize will do. Each event in this table belongs to a user and has a session ID. Each session begins with a start event and ends with a pause event. In addition to start and pause events, there is one other event type, and that's a buffering event. These buffering events indicate that the user experienced a hiccup in video playback. The playback device waited for the stream to be rebuffered. This table shows 2 sessions, the first of which had no buffering events, while the second session had 2 buffering events. Of course, occasional rebuffering is just normal and can be caused by issues in the user's networks. But widespread service degradation is something the video-on-demand service operator will want to investigate. This match recognize pattern captures how this stream works. Each session has a unique session ID that we will use to partition the stream. The events should be ordered according to the event time column, and each session begins with a start event, ends with a pause event, and may have any number of buffering events in between. The measures section is where we can capture the session-based analytics we are interested in. The buffering events that match the variable b are a group we can aggregate over. Here I am counting the number of buffering events in each session. And here I can measure the duration of each session by computing the difference between the timestamps of the start and pause events, as measured in seconds. Match row time is a special built-in function. It returns a time attribute for each row in the output. The timestamp of this time attribute is the timestamp of the last event in the match. Or in other words, it's the timestamp of the pause event that ends each match. But match row time is more than a timestamp. It's a time attribute. This means that it also has watermarking defined on it. So we can use this time attribute to apply additional temporal operations to the output of match recognize, such as windowing. I'll show an example of this in just a moment. But first I want to show you how the output table looks. Each row of the output corresponds to one instance of the pattern having matched a session. The output is reporting the number of buffering events, the duration of the session, and there's the time attribute. I've called it S time. Now this rather complicated query is using the match recognize logic we've just been looking at to count the number of buffering events in each session, and then putting those results into tumbling windows that compute the average number of buffering events in the sessions that ended during each window. Most of this is the match recognize query from before. Here I've used a common table expression to give that match recognize query a name, which is used as the table being fed into the tumbling windows. And here you can see that the time attribute produced by match recognize is being used as the time attribute for the tumbling window function. Now I want to share some things to keep in mind when you're working with match recognize. First of all, the input to match recognize must be an append-only table. Using match recognize with an updating table, such as the output of a regular aggregation or a regular join, that isn't supported. If you try, it's going to result in an error. But the output from match recognize is itself an append-only table. This is very convenient, as it means that there are no limitations on how you can further process the results produced by match recognize. Of course, for simple patterns, you may be tempted to use a self-join or an over window instead. The fact that match recognize can produce time attributes is a very good reason to prefer this approach over a join. And finally, because match recognize does sorting, it adds latency to your stream processing pipeline. How much latency it adds will depend on how much out-of-orderness your watermarking strategy can accommodate. It's also the case that late events will be ignored. As for best practices for working with match recognize, you need to keep in mind that match recognize keeps state. The Flink SQL runtime has to keep track of every partially matched pattern. Consider, for example, the pattern we looked at first, the one that looks for customers who place 2 orders for the same product within 60 days. To do this, the runtime has to remember every unmatched order from the past 60 days. That could be a lot of state, but without this time constraint, it would be much worse. This is why it's a best practice to guarantee that every pattern will eventually end. In the first example, we did this by constraining the matches to be found within 60 days. In the third example, the one with video playback events, we are confident that every session will eventually end with a pause event, so we don't expect to have any permanently lingering, partially matched sessions. Now it is possible for match recognize to behave non-deterministically. This can happen if your input stream has events with the same timestamp. This will make the sorting non-deterministic, unless you have provided a secondary sort ordering in the order by clause. Someday you may find yourself debugging a match recognize query. This probably means that the query is failing to find any matches. Here are a few ideas that have helped me. First, remember that the sorting match recognize does relies on watermarks. So you want to check that watermarks are being produced and that they are advancing. For more on debugging problems with watermarks, see the resources linked in the description below. Now, could it be that your pattern can only be satisfied by an event that hasn't arrived yet? Double check that your pattern is guaranteed to terminate. My experience is that it's surprisingly easy for patterns to behave in subtly different ways than what I expect. So what's helped me most in debugging these situations is to simplify the pattern to the point where it definitely produces output, and to include additional columns in that output that help me check my assumptions about what's being matched by the different variables defined in the pattern. When your pattern includes a variable that might match many rows from the input, the array aggregate function is a convenient way to capture information from those rows for debugging. Earlier, in the example with prices that go up and up, I used the array aggregation function to verify that the prices of the matched orders are indeed rising. In practice, I would probably do something more like this. Each element in the array is actually an embedded row containing various details of the matching order. The built-in row function constructs a new row, and here I've used a cast so that I can name the fields in these embedded rows. Thanks so much for watching. If you want to experiment on your own, don't worry. You don't have to try to scrape the text for these examples out of this video. The code for these examples and other related content, it's all on the Confluent Developer website. You'll find a link in the description below.